2nd September 2023, 11:50 a.m. Save the date, because India is all set to make her tryst with the sun. In ancient Indian texts, the sun is considered as God. In medicine, the sun is a nurturer. Doctors advise soaking in the sun for vitamin D. In physics, the sun is a source of light, energizing everything that comes before it. How do astronomers see it? A star and an almost perfect ball of hot plasma. And it is this sun that Indian scientists are now aiming for after their historic rendezvous with the moon. Aditya-L1, the first Indian space mission to study the sun, will be launched this week. The spacecraft will be placed in what is called a halo orbit around the L1 point. Now, what is this L1 point? L1 stands for Lagrange point 1. It's about 1.5 million kilometers from the Earth. So Aditya-L1 will be traveling a distance of 1.5 million kilometers to study the sun's atmosphere. The total travel time from launch to L1 would take about 4 months. Now remember, Lagrange points are named in honor of Italian-French mathematician Joseph Louis Lagrange. And these Lagrange points are positions in space where two or more gravitational forces produce more attraction and repulsion. Now, these spots can be used by spacecraft as parking spots in space to remain in a fixed position with minimal fuel consumption. Our sun is surrounded by a jacket of gases called an atmosphere. The corona is the outermost part of the sun's atmosphere. But the corona is usually hidden by the bright light of the sun, and that makes it difficult to see it without using special instruments. Now, this corona is much, much hotter than the surface of the sun, and that is what makes it so difficult to study and research upon. This corona is what Aditya-L1 largely aims to study. Remember, apart from India, Japan, China, NASA, and the European Space Agency are the only ones who have sent their sun missions so far. Now, since this is such a vast, complex subject for people like us to understand, let me take this across to my guests tonight. I'm joined by Mr. Suresh Naik, former Group Director of the Indian Space Research Organization. Mr. Naik, good evening. Namaskar, sir. Welcome to Mirror Now. Vinod Srivastava, former ISRO Scientist, also joins us. Mr. Srivastava, good evening. Welcome to Mirror Now. And Dr. Vagish Mishra, Assistant Professor at the Indian Institute of Astrophysics in Bengaluru, also joins us. The Indian Institute of Astrophysics, remember viewers, has worked on Aditya-L1 along with the scientists at Indian Space Research Organization. All right, let me take this across to Mr. Naik first of all. Mr. Suresh Naik, this of course, Aditya-L1 comes after our historic success and rendezvous with the moon. But now the focus is on the sun. First of all, in simple language, sir, for our viewers and for people like me who don't understand the technicalities of space and astronomy, help us understand why it is so important for us to send a spacecraft and study and observe the sun.
Yeah, actually, first of all, I can say that there is no respite for the Indian population from the excitement, because it's a back-to-back mission after the stupendous Chandrayaan.
And we are not complaining, sir. We are not complaining at all. Please keep bringing this on.
Yeah, so what I'm going to say, to start with, I think let us explain to the viewers, why this space-based observatory. Already we have got a lot of good observatories on the ground. But the limitation in the ground observatories or ground telescopes because there is an atmosphere in between, and the radiations coming from sun or the UV ultraviolet wavelengths, they get absorbed, most of them, in the atmosphere. They don't reach these Earths, most of them. And there is an interference due to atmosphere. As because of that, the clarity is not there as much as it is required for observing the celestial objects from ground. Another thing, observation in daytime is impossible from the ground telescopes, whereas it is possible if you keep the telescope outside the atmosphere, where there is always it is possible to observe sun or any other celestial objects. And most important thing is, you mentioned this is Lagrange 1 point is where it is going to be parked. The most advantageous aspect of that is it is going to be stable, and there is not going to be a solar eclipse in that area. And I want to tell viewers that every year there are 2 solar eclipses take place for geostationary satellites. And these solar eclipses, they stay or they live for about 3 weeks every time. So 6 or 7 weeks of precious time in observation is lost if it is not based in the space. Another advantage of the space-based observatory is it has got very powerful resolution and very powerful detecting ability. That means the sensitivity is very high. And because of these 2 things, they can have the capability to reach a very long distance for observation. So these are the advantages of the basically having a space-based observatory. Now let us come to the objectives. Okay, the first objective is monitor solar activity. Now, what is solar activity? There are flares, the heat flares, the light flares are coming out of the sun very frequently. And this Aditya-L1 satellite experiment, there are going to be 4 experiments on the satellite, 7 experiments total. 4 of them are going to be constantly looking at sun, and 3 of them are going to study the L1 Lagrange point. Now, these sensors on the satellite looking towards sun, they will help in the study and in the prediction of space weather events. What are the space weather events? They can be, this solar radiation reaching Earth and causing impacts like our satellites which are already in space. These impacts can cause the change in their orbit. They can also reduce the life of our satellites, and they can create blackouts, power blackouts on the Earth. They can also disrupt our communication system. So these are very impactful events, and we want to study them so that we can predict and then take precaution. Actually, we have done this before, and we can put the satellite in safe mode and things like that. And then this
essentially, sir, then basically we're looking at what happens in space and the impact of the sun on Earth as well. These 2 impacts we are largely looking at through Aditya-L1, if I've understood correctly. Let me go across to Mr. Vinod Srivastava also. Mr. Srivastava, there's a lot of talk about the payloads on this spacecraft and why they are significant, how they're different from earlier when we had tried, and how are system and how our spacecraft this time around is helping us study more number of subjects than what we initially started out with. Help us understand, sir, what's the difference and why are the payloads significant this time?
See, when you do any measurements from our Earth, there is a lot of interference, electromagnetic interference of the surrounding area. When you go to the upper atmosphere, let us say 300 kilometer or 600 kilometer, some of the interference get reduced, but the stealth is still maintained there. If you go wanted to measure anything, you go as near as possible to that particular planet. Let us say if you want to go to the Mars, if you want to go to the moon, if you do the measurement from near the surface, so all the surrounding interferences will be minimized or becomes almost zero. So when you go wanted to do something about the sun, we can do it right from here, as Suresh Naik has said already. So when you go as near as possible, then our instruments will measure without interfering or without getting any other signals from the other sources which are generating from there. So it will give you very good measurements. So these are the reasons why we want to go as near as possible. Now, why we have chosen L1 place? Now let us see what is the rockets we are having. So I want to give one just small example. If we have two cars, one is nano car and the other car, and you want to go from Kanyakumari, or you want to go to Manipur, or you want to go to Kashmir, you have navigation, guidance, and control system. If you are master on these things, because human brain is master about knowing all the directions, control with the car, using the accelerator and everything. Now we have done the mastery on these three systems. So wherever we want to navigate our satellite, we want to guide it, then we have a powerful rockets on this satellite. So what we are doing, we are lofting a satellite using our horse rocket, that is a PSLV. This time we are named as a C-57. This will put the satellite in a geo transfer orbit. After getting the orbit, this will perform the same type of maneuvers as is done for the Chandrayaan. When it gets the sufficient velocity where we can leave this our gravitational force and goes towards the sun. So that is the thing. We sent 1.5 million, as you told already at the beginning. It is going to take around 4 months. With the velocity, when it goes there, reaches near the L1, where, as you mentioned, there is a gravitational force of the sun as well as the earth is almost balanced there. So any satellite, it can move in that particular orbit with a much lower speed. Since we have to escape our earth velocity, it has to go near about 11 kilometers. When we reach to L1 point, even less than a kilometer per second speed, we can move around that L1. So it may take about it will take one revolution around the L1, very long time, maybe I think 3 to 4 months. In 3 and 4 months, all the instruments are directly measuring the sun's disturbances, wherever the flares are coming, what are the electromagnetic radiations are coming from the sun. It measures from there, converts into units, and sends back to the ground for our measurements. So this is the way we wanted to go as near as possible to observe the differences of the satellite near the Earth, near the sun.
Okay. All right. Dr. Vagesh Mishra, you're from the Indian Institute of Astrophysics, the institute which has been part of the Sun mission. What has the contribution been in terms of the setting up, the manufacturing, or how it operates there up in space?
Yeah, so regarding, as the other esteemed scientists have told, that this mission has 7 payloads, 7 main instruments. So one among the instruments is the VELC, Visible Emission Line Coronagraph. So first, I would like to explain for the viewers what is coronagraph. So coronagraph is basically an instrument which creates artificial eclipse. When there is a natural eclipse, the moon exactly occurs the disk of the sun. And what we see is the outermost atmosphere of the sun called corona. So scientists have developed a technique to artificially eclipse, occult the solar disk so that we can constantly see the corona, outermost layer of the sun, because natural eclipse happens so rarely and only for a few minutes. And in that time, it is very difficult to take enough observations to understand the solar corona. So for that purpose, coronagraph is an instrument which can create artificial eclipse and always look at the coronal structures. So there is a history of coronagraphs. Lyot, one scientist, started this invention, and it has been used by other space agency, NASA, and European Space Agency, ESA. But India has come up with a very unique concept, and they have made a coronagraph called visible emission line coronagraph. So this idea of coronagraph, if I would like to go a little bit in the history, so in the Indian Institute of Astrophysics, many senior professors, including Professor Jagdev Singh, they actually imagined that India should plan for a coronagraph. And this is long back before 2010. This was the first conception made. And then, of course, senior people go out, but they train the next generation. And a lot of scientists in IIA are involved in understanding first the concept, how it should be, and finally, over a long time after the dedicated scientist working on this payload, finally the VLC was designed and design was made, and then this payload was approved, and it was made in one of the laboratory of the Indian Institute of Astrophysics, that is called MGK Menon Laboratory, that is also based in the Bengaluru. So in that observatory, this payload was made, VELC, Visual Emission Line Coronagraph, and it has a very unique concept, which no other earlier coronagraph, if you see, like NASA has launched several missions which had coronagraphs, but this coronagraph of India on Aditya-L1 mission can see the closest layer, closest of the solar corona. So most of the earlier coronagraphs have not seen the inner corona of the sun, the corona which is just above the photosphere, chromosphere. That layer has been unobserved in last 2 decades, 3 decades actually, after having several missions from NASA and ESA. But this VLC has a unique capability to look at the inner corona constantly, and not only in the imaging the corona, but this VLC actually also has a spectroscopic observations of the corona and spectropolarimetric observation of the corona. So such observations will actually help us to understand what actually hits the corona. As viewers might know, that the outermost layer of the sun, which is the corona, has temperature at least 1,000,000 degree Kelvin, but the photosphere, which is the layer below that corona, is only 5,000 Kelvin. So scientists are still wondering to understand why the outermost layer of the sun is so hot. And this is one of the main objectives, to understand why solar corona is hot. And as other scientists from ISRO has also explained, that from the sun, there are energetic expulsions of plasma blobs. So it happens sometimes on a periodic basis, episodic basis, that sun actually release billions of tons of mass altogether. And if that mass comes away from the sun, it travels into the solar system, passing through Mercury, Venus, and Earth. Sometimes if it is directed towards the Earth, as Earth is orbiting around the sun, such billions of tons of plasma, which is launched from the sun with a speed ranging few hundred to few thousands kilometers per second, if that reach to the Earth, it can damage the space technology. It can damage the space technology, ground-based technology, transformer can be damaged, and communication, GPS, several things can be damaged. And as our dependence to the technology is increasing day by day, it is very important to protect the space technology, ground-based technology. And in that case, we need to monitor what are the conditions on the sun. And this whole branch of science, astronomy, which scientists are doing, is now termed as space weather. Space weather means weather in space. So I would like to give one more minute to the explanation. Like in the terrestrial weather, we predict that tomorrow what is going to the weather, humidity, rain, sunlight, heat. In the same way, scientists are trying to predict the weather in space. So on the ground, actually, we stay. Humans stay. So the terrestrial weather affects the human, and this is why weather forecasting is done. But in the space, there are satellites, space technology, and we need to care about them because our dependence to space technology is increasing day by day. And if they are affected, we will be severely affected. So in space weather, we try to
Yeah,
understand what are the
absolutely.
conditions
So,
on the sun.
interesting point there. Yeah. Yeah, interesting point there that it's quite. I mean, I'm very curious to actually understand why the outermost layer of the sun has to be the hottest, because it's just reverse. It's usually the hottest when we go inside. A hot ball of plasma, as we call the sun, but it's the reverse, and that's what Aditya-L1 also aims to do. One of the aims, of course, is that. But Mr. Suresh Naik, this I believe is a long mission. It's about 5 years, and we're covering about 15 lakh kilometers. And please do correct me if I'm wrong here. Out of a total of about 15 crore kilometers that the Earth and the Sun have, that distance. In this, what are the kind of challenges that Aditya-L1 might face in its journey?
Yeah, actually, for this particular mission, ISRO is going to use its less powerful rocket, which is PSLV, which was used for Chandrayaan-1 and Mangalyaan, not LVM-3, which was used for Chandrayaan-2 and Chandrayaan-3. Because here, our mass of the satellite is not that big, and it is within the capability of PSLV. Secondly, that reduces the cost tremendously. At the same time, we have to see that the satellite travels a very, very long journey, 15 lakh kilometers, and that we are going to achieve by our now well proven technique of first launching the satellite in a near or the Earth orbit, like we did in case of Chandrayaan 3, something like 30,000 kilometer by 180 kilometer or so. And then, having done its job, the PSLV rocket would fall into the ocean stage by stage. After that, now the satellite, with the help of the fuel inside it and the engine which has been provided on that, has to travel all the way to 15 lakh kilometers. How it will do that? You see, we know now because of Chandrayaan 3, your coverage and other channels coverage, that we have established the technique of firing the engine when the satellite is at the closest point from the Earth, which is called perigee, and taking the assistance of gravity of the Earth, we increase the apogee, which is the farthest point to the from the Earth, and we are going to proceed to Sun like that. And this firing will be done many times, so that gradually this orbit goes on rising. Now, having done that, as earlier has been mentioned by the IIS scientists, when we fire ultimately the engine once again after the satellite has reached the highest point in the Earth orbit, then its velocity will increase to a value of 11.2 kilometers per second or 40,000 kilometers per hour. That enables the satellite to get out of the Earth's gravitational influence. Or in other words, that is an escape velocity of the Earth, and then it can start traveling towards Sun. No problem. It will not come back to Earth then. We are sure about it. And then it takes 4 months with that high velocity to reach that L1 point, which is 1 million kilometers from Earth, and is almost 100 times more distance is still remaining between the satellite and the sun. So we are safely away from the sun's highest temperature in the corona. So that is how we would have cleared all the challenges of reaching first in the L1 point. Now, L1 point, as has been already some points have been mentioned, one more important aspect of L1 point is its orbit is stable. That means it is not going to be disturbed because of any gravitational forces of any celestial objects. So otherwise what happens is normally when a satellite is in the lower orbit, the influence of the sun's gravity, moon's gravity, and other celestial objects' gravity has an impact on the orbit of the satellite, and it tends to drift from its given orbit. And then you have to spend fuel to make that correction very often. And in that making correction, you are spending fuel. So in this particular case, ISRO has really come out with a very good idea of choosing the L1 point for parking. Now our energy required is going to be minimum, so that increases the life of the satellite. So you can see we have achieved a low cost mission, we have achieved a longer life, and we have chosen 7 payloads in such a imaginative and brilliant manner that we are expecting that we'll come out with some significant new research about the sun. One point which has been left out, I would mention about the objective of this mission is have actually a measurement or study of the sun's magnetic field, which is also extremely important. And that will also be tried in this particular mission, and shedding the light on origin and dynamics of solar magnetic activity. See, this is very important, so that then we come to know what it will be impact on the Earth. One more thing I want to mention, why actually this thing happens. What is the unique thing about this? You see, sun being our parent star of the entire solar system, it has got an influence on all the other planets in the solar system, not only Earth. Okay, and that influence actually in the long term creates a lot of problems. Like earlier mentioned, our satellite's orbit gets disturbed, satellite life gets affected, our power system grid can get breakdown, and it can cause a power blackout on the Earth. So such serious consequences can happen because of Earth's space weather.
Yeah.
And that is why this study is going to be extremely useful in future. And another important thing which I want to mention is we are going to use a wavelength band of ultraviolet rays and X-ray. Now, what is the special thing about this X-ray and ultraviolet band going towards the universe is because they can go through, penetrate the dust clouds which are there far away. In fact, NASA has sent already a James Webb telescope, and they are finding now that dust clouds are a great hindrance for the clearer observation of the galaxies. Now, we are in a position to penetrate through these clouds, dust clouds, and go to the far distance. And maybe, I think a good research will come out of this, discovering of galaxies or other celestial objects, star formations, and things like that. So what I want to say is ISRO always tries to attempt to do new things, in their every mission. And we know already we have discussed a lot on Chandrayaan 3
which is
mission.
what we have seen in Chandrayaan 3. And of course, with new components and new elements coming in Aditya-L1 too, we are seeing that ISRO scientists and, ISRO is working hard with new elements. My last question to you, Mr. Vinod Srivastava, quickly, if you could, share your perspective on India's space exploration journey. We are seeing, we've made this huge historic comeback with Chandrayaan-3. Now we have Aditya-L1. How do you see India's space exploration journey really panning out?
Yeah, we started with the PSLV with a mere 1000 kg of payload in a low Earth orbit. In the parallelly, we have seen the capability of this rocket can be enhanced by using the strap-on rockets with the XL, and we have reached to the capability of 1750 kg of satellite we can put in a GTO. That is from nearest to the Earth is around 170 kilometers and the farthest say around 36,000 kilometers. So this technique we have used by sending the satellite in the outer atmosphere or the outer space using the fuel of the satellite. It has to be mentioned there, whenever the satellite is in space, it will have always control in all the three axes, that is called the roll, yaw, and the pitch. It should never be removed from there. Parallelly, we have developed a deep sea radar which can communicate with the satellite throughout the journey. Now, wherever we want to send the satellite, after removing from the rocket, we use the fuel of the satellite, which is almost half the quantity of the satellite. Let us say the satellite is weighing say 1000 kg, so more than 500 kg of the fuel will be there, which will be used from the GTO orbit to put in the space. Now, as you ask, the challenges what the satellite faces or this Aditya faces in a 4-month journey. You will be surprised that in 4 months journey is never left without any control. The control will be always with the ground stations. It has fitted with the larger rocket. It has fitted with the micro rockets, which may keep it stable and always go on thrusting it in such a way it goes toward the mission of the L1. So in no time of the journey of the 4 months or even after 4 months when it is rotating around the point L1, it will never be left without any of the guidance and the control of the system. Since we have mastered on the system, that is the control guidance, and in the system is helped us to send a satellite in the whether in the lower orbit about 300 kilometer or 600 or a GTO or a mission towards the Mars, the mission towards the moon. Now we have taken emissions towards the L. Now their times are not far, like the other space, like NASA is to send the probe which goes in the space without any planet running for months together. Now, since we have certain things we have to develop, where we have to get the power to the battery power to always to the spacecraft. So, since other countries having that particular type of battery which runs on the nuclear principle, now I understand ISRO also is developing that system, and very soon we will replace the solar charged batteries to these batteries which are developed on the nuclear-based technology. So with this, we'll be able to explore
so
other parts of the space.
From where we started, from the cycle to the sun, now we've come a long way, of course. We all know, how we started carrying our rockets, our PSLV on cycle, and today we're sending our spacecraft to the sun. On that note, I am going to thank my panelists. I'm going to wrap my discussion up. And of course, I hope that Aditya-L1 is as successful as Chandrayaan-3 and India's space journey, space odyssey, space rendezvous continues as successfully as it does. Thank you very much, Mr. Vinod Srivastava, Mr. Suresh Naik, and Dr. Vagish Mishra for joining us tonight and helping us understand better what ISRO's next sun mission, Aditya-L1, is all about. Thank you very much, gentlemen. With that, we're slipping into a short break. News and updates will continue on the other side. Do stay tuned to Mirror now.